You got mvx is the momentum as it collides. Negative mvx is the momentum after collision. The change in momentum will be 2mvx. Suppose you consider a time interval delta t. All the molecules in a volume AVX delta t will reach the area in that time. Do you understand that? You see, if this molecule has a velocity v, what does it mean? It means it will travel a distance v in 1 second. So from here, in 1 second, it will reach there. That means it travels a distance v. So if there are many molecules in this area, during that time, all those molecules would have reached the wall. So if you consider a time delta t, look at the volume AVX. What does AVX tell you? A is the volume of the box. Vx is the velocity of each molecule. So if this molecule is going to reach the wall in 1 second, that means all the molecules along with it and in front of it will also reach the wall during that time. So the volume, this is the volume A times Vx. See, this is the length Vx. In 1 second, all the molecules in the volume A times Vx will all reach that wall. And therefore, in a small interval delta t, the molecules in this volume AVX delta t, all those molecules will reach the wall in that small time interval delta t. Alright, but at any given time, only half the number of molecules are likely to be moving to the right. The other half will be moving to the left. Therefore, we need to make an adjustment here. The number of molecules reaching area A in that time delta t will be 1/2 of this. 1/2 of A times Vx times delta t. And of course this is the number of molecules per unit volume. So if you multiply this with the number of molecules per unit volume, that will give you the total number of molecules reaching that wall, and only half of that will be likely to be moving to the right. The other half is moving to the left. So what does this quantity represent? This quantity represents the number of molecules that is likely to hit the area A during that time delta t. Now, the change in momentum of all these molecules, this is the number of molecules that reach this area A in that small time interval delta t. And each molecule suffers a change in momentum given by how much? Each molecule suffers a change in momentum mvx minus negative mvx, which is 2mvx. So if you now multiply this quantity with 2mvx, that will give you the total change in momentum experienced by all these molecules. So the total change in momentum experienced by all the molecules that reach this wall of area A in this time interval delta t is 1/2 n over v a vx delta t. That is the number of molecules reaching the wall in that time, multiplied by the change in momentum of each molecule, that is 2mvx. What does that simplify to? Well, the 2 and the 2 goes, and vx will multiply by vx will give you vx squared. That is n over v am vx squared delta t. What does this represent? This represents the total change in momentum that happens at this wall during this time interval. Alright, so this is a measure of the total change in momentum during this time interval. Therefore, what is the rate of change of momentum of these molecules? The change in momentum divided by the time represents the rate of change of momentum. So delta px divided by delta t, that gives you n over v am vx squared is a measure of the rate of change of momentum. Alright, what did we say Newton's second law is? The rate of change of momentum is a measure of the force exerted on the wall. According to the Newton's second law, this rate of change of momentum is a measure of the force exerted by these molecules on the wall, because the change in momentum happened because the molecules hit the wall. You see? So that rate of change of momentum is a measure of the force exerted by all these molecules on this wall. Therefore, we can say if Fx, we are now considering only the x direction. If F sub x is the force exerted on the area A by these molecules, we can say F sub x equal to n over v am vx squared. Well, now look at how a theory takes shape from mere assumptions. Don't you admire physicists and chemists who work and obtain these kind of beautiful relationships based on imaginations? Alright, that's how science works. That's how science grows. And that's the reason why we say science never gives you the absolute truth. It gives you avenues to explore continuously. So all these theories are subject to questions, subject to change. That is the premise of science. That is how science works. The pressure exerted by the gas, therefore, the pressure exerted by a gas. You see, this is a measure of force. Force exerted by those number of molecules on this wall of area A. What is the definition of pressure? I hope you remember. Pressure is defined as force per unit area. So if you know the total force acting on a certain area, that force divided by area will give you the pressure. Pressure equal to force divided by area. So let's divide both sides of this equation by A. You can f of x divided by A will be n over v m vx squared. So pressure is force divided by A equal to n over v m vx squared. Alright, there we have an expression for the pressure. But is that the final version? We have only considered the x motion. Well, from here you know cross multiply P times V equal to nm Vx squared. But you know that PV equal to NNAKT. You remember that one? PV equal to nRT, where R is Avogadro's number times Boltzmann constant, Na times K. So PV equal to N the number of moles, Na the Avogadro's number, K the Boltzmann constant times T. That is equal to N times Na, the number of moles multiplied by the number of molecules per mole. That N times Na is the total number of molecules. So what do we have now? we have PV equal to NKT, where N is the total number of molecules, K is the Boltzmann constant, T is the absolute temperature of the gas. So NKT equal to NmVx squared. How did I get this one? Look at this. PV equal to NmVx squared. That is what we have been working hard so far to obtain. And this is the result that we already know from ideal gas law. So ideal gas law tells you that PV equal to NKT. From our assumptions, we obtained PV equal to NmVx squared. So if our assumptions are right, then this NKT must be equal to NmVx squared. Is that right? Okay. That means K times T equal to, that means N, the big N, the number of molecules on each side will cancel. We get K times T equal to mVx squared. That's an important relation. Now, if K times T equal to mVx squared, then 1/2 kT will be equal to 1/2 mVx squared. Why did I do that? Because we are so familiar with this quantity, 1/2 mv squared. 1/2 mv squared is a measure of the kinetic energy of a molecule. You see, Vx stands for the x velocity of the molecule. mVx squared is the kinetic energy of a molecule moving in the x direction. So 1/2 mVx squared is a measure of the kinetic energy of a molecule moving in the x direction. And what is that equal to? Equal to 1/2 kT. The energy of a molecule in the x direction is 1/2 kT. I want you to remember that one. All right. Average kinetic energy due to the x motion equal to 1/2 kT. That means average energy due to y motion also will be 1/2 kT. Average motion due to z direction motion also will be 1/2 kT. That means average energy due to each type of motion, x motion, y motion, z motion. Each of these motions will give an energy of 1/2 kT. But the molecule is equally likely to move in the x, y, and z directions. Therefore, Vx squared can be approximated as 1/3 of the square of the actual velocity. You see, this Vx squared, if the velocity of this molecule is in any arbitrary directions, it is made up of Vx, Vy, and Vz. Therefore, we can consider this Vx squared as 1/3 of the square of the average velocity of the molecule. So how do we write that? If V bar is the average velocity of the molecule, you remember we started with that assumption. V bar, V with a line on top, is V bar, is the average velocity of the molecule, then this Vx squared, that is the velocity in the x direction, is 1/3 of that V bar squared. Does that assumption make sense? I think so. So, this Vx squared can be now replaced as 1/3 V bar squared. The average kinetic energy of a molecule, therefore, is given by K average is 1/2 mV bar squared. This is the average kinetic energy of a molecule, where V bar is its average velocity. Now, I'm going to replace this V bar squared. Look at this. This V bar squared is replaced by 3Vx squared. Because we said Vx squared is 1/3